Hey there, Brett. So, we just finished up simple and compound machines last week. In fact, you just completed a project where you were supposed to take a compound machine and break down all of the simple machines in it and explain how those simple machines help the compound machine work. The reason we did that was, well, to give you some experience with something that we thought would be most useful to all of our students moving forward, not just those students who might be going off to an academic career in college or something like that. Simple machines, at the very least, will help you move things around your house more easily. But if you really understand how to use simple machines, you can manipulate your environment in many ways that would be inaccessible to you without them. Basically, human beings are weak and we need help. So that's why we decided to finish off the force and motion unit with simple machines. We didn't want to just leave you with Newton's laws because, duh. But instead give you something a little more useful. So hopefully that was enjoyable. I know we carried quarter two's work into quarter three a little bit, so we are losing out on quarter three a bit. But that's okay. So what we're going to move into was what we originally had planned for quarter three, which is chemistry. Now, obviously, being in the situation that we're in, we're not going to get deep into chemistry. We're going to cover some of the basics. I'm going to try and give you a bird's eye view of the chemistry subjects. Some of them we might go into in a little bit of detail, but really the goal of this particular unit, this chemistry unit for quarter three, is to get you ready for chemistry potentially. Most of you, even if you decide to take some of the easier science courses, will end up in chemistry in your junior year. So we want to give you some of the tools that you're going to kind of need to understand what the heck Miss Martin's talking about. Because chemistry can be intimidating. I know for me, chemistry has always been my weakest science subject. So it can be complicated. It's a lot of memorization of different rules and different things. You basically kind of have to turn yourself into a chemical dictionary if you want to be a chemist. But it's also something that if you're not interested in an academic sense, understanding some of the basics can just help you understand things like cooking or cleaning around the house and other things like that. So try and take something from this. If you don't plan on being an academic, try and take some of the basic concepts from this that might be useful in the future just in your everyday life, like mixing acids and bases. Well, they make something happen. Or I'm not going to get into examples. I'll stop rambling. Let's just go on ahead and get into what we're going over this week. So this week is all about an introduction to chemistry, and really it's an introduction to matter, atoms, mixtures, solutions, and things like that, molecules and whatnot. We're just going to kind of define terms this week and get a sense of what it is we're talking about. So, chemistry is the study of how atoms and molecules interact with each other. That's really it. Now, chemistry doesn't describe physics in terms of like this molecule here is moving across and it collides with this molecule here and then we describe what happens. No. This is about mixing different atoms with other atoms and getting them to bond to each other, or to break bonds of atoms to release energy or to get us a new substance. So chemistry is all about rearranging atoms and how they're connected to each other. And there's a lot of reasons we would want to do that. Cooking, cleaning, driving, breathing, digesting your food, burning anything. Thinking. If you're playing games, running around, you're burning energy. Well, that energy is coming from chemicals inside of your body. In fact, you are a walking bag of chemicals. And the reason you're able to do all of the things you're able to do is because there's chemistry going on inside of your body that's giving you the energy to do it. And if you don't consume food and you don't consume water and those things, well, you run out of energy very quickly and your cells die and you cease to be. So you are a walking, talking chemistry experiment, so to speak, or chemical reaction. So you can't get away from chemistry. It is really, it's the reason why we're around. Obviously, the study of chemistry is the study of matter. And what matter is basically anything that takes up space. Right now, there's matter floating around and colliding with my noggin all the time. It's called the air. And you are surrounded by it, and it takes up space, and you can fit it into a jar, and you can compress it, and you can, use it to spray off your keyboards and everything else. Like air is matter, and it takes up space. You are made of matter. You take up space. anything you can touch or interact with in any way is basically made up of matter. Now, all matter is made up of atoms, which is the smallest possible unit of matter that still kind of maintains some unique characteristics. So hydrogen is an atom, and it's an element as well. It's a very particular element, and it has one proton and sometimes one electron. We'll get into that stuff in a minute. But matter is just stuff you can touch, interact with, so on and so forth. And the smallest unit of matter, as I said, is the atom. And it's the smallest unit of matter that still retains individual properties. So I say that, and here's what I mean. I can take an atom and I can actually split it. But when I split an atom apart, when I break it into even smaller bits, it breaks down into things like gluons and quarks and things like that. And those things are unstable, they unravel, and they don't exist very long. We do this with the particle accelerator, and there's several of them. You can look up a particle accelerator if you want. Basically, we take little tiny things and we make them go around a giant loop that's several miles long and mash them together at speeds approaching the speed of light. And then we see what happens when they break apart. And we create all these little tiny particles that atoms used to be made of, but those little tiny particles, well, they pop out of existence very quickly. They basically turn back into energy. So the point being is that atoms are as small as you can get before things kind of break down into something that, well, doesn't stick around very long. Now, you cannot destroy matter and you can't create matter. I know I just said you can break an atom apart and then it kind of fizzles out into it turns into energy. So you can convert matter into energy, and that's what we do with nuclear bombs. We split an atom in half and it releases a ton of energy. So you can convert matter into energy, and that's what Einstein kind of taught us. But for the most part, you can't destroy matter, you can't create matter. So with chemistry, anytime we're reacting things, we have to have the same amount of stuff that we started with at the end of the chemical reaction. It might change form, it might turn into a gas, and it might seem like it disappears. Like if I take paper and set it on fire, well, it turns to water and CO2. That doesn't mean the matter disappeared, it just turned into a different form. So keep that in mind. We can change matter, but we can't destroy it or create it. Anyways, each atom has its own unique properties. So if you look at the periodic table of elements, which we'll see here in a few minutes, every single atom has different properties, every single element. So if I have one proton, I'm hydrogen. If I have two protons, I'm helium. If I have three, I think I'm boron, something like that. Anyways, lithium. So each different atom has different properties, and we'll kind of get into those at another time. Okay, so there are different parts of the atom, just as there are different parts of basically anything out there. And the parts of the atom are such. So you have a nucleus, and the nucleus is at the center of the atom. And the nucleus is made up of protons and neutrons. Now, a proton is positively charged, and a neutron has no charge at all. That's why they're called neutrons. N-E-U means neutral, right? That's where we get the word from. And proton, pro, means positive. So protons are positively charged. And the reason why we have neutrons in the center of the atom is to help space out the protons. Protons don't really like each other. It's the same thing as electrons don't really like each other. They don't want to be near each other and they don't want to touch each other. If you've ever had a magnet, if you take the north side of a magnet and the north side of a magnet and try and put them together, they push each other away. And this is what protons do when they're in the center of a nucleus. They want to push each other away. So what neutrons do is they're basically like the glue of the nucleus. And they kind of space out the protons and give them all the space that they need so that they don't rip each other or rip the nucleus apart. Basically, they're the peacekeepers. They're there to glue. They're to keep it all together. And if you have too much glue, just like if you have a project and you pour way too much glue on it, things tend to be unstable. They tend to run off the paper, right? They don't stick. Same thing is true with neutrons. If you have too many neutrons in your nucleus, it becomes unstable and it will split or break apart. The same thing is true if you have too little. So if you don't have enough neutrons, it's still unstable because you're not now spacing the protons out. So generally with the smaller atoms, the smaller elements, you will have almost an equal number of neutrons as you do protons. As you get bigger, you can hold a few more neutrons than you can protons. And when you get really big, you can hold quite a few more neutrons than protons. Things like uranium have a lot more neutrons than they do protons. But things like helium have the same number. And if you add 3 neutrons to helium instead of the normal 2, it becomes unstable and it breaks apart. So, long story short, that's what the neutrons are in there for. Now, the things that you have seen, so this model of the electron, you see the little orbitals here. This is an old model, but it's one that kind of helps us visualize atoms a little bit easier than some of the older models. Really, electrons aren't flying around like that in real life. They actually create this field, or kind of like a cloud, around it. And electrons are actually kind of blipping in and out of existence and popping over here and popping over there and popping over here and popping over there. They're weird. But to simplify things, we've created this atomic model that looks like you have these orbitals, these little loops that the electrons float around. Point being, the electron is on the outer part of the atom. It makes up the part that you touch. So when I take my hand and I touch my desk, or I press against my desk, it is the electron forces that are repelling my hand. They're pushing my hand up. Otherwise, my hand would go straight through the desk, right? So the electrons are there. They're kind of like the barrier. They're the outside shell of the atom. And most of the inside of an atom is actually empty space. Atoms are 99% empty space. So there's a lot of space between the tiny little nucleus in the center and these electrons that are floating around on the outside. So the electrons are there kind of providing that barrier. They're also what causes atoms to stick together and bond to create molecules, which we'll get into eventually. So electrons are really important. Now they're negatively charged, okay? So protons, remember pro means positive, they're positively charged, and electrons are negatively charged. And the cool thing is that you will have the same number of electrons as you do protons, most of the time. So, or ideally. So if I have a carbon atom, so carbon has 6 protons, it also has 6 electrons, and they cancel each other out. If you have more electrons than you do protons, well, you're considered negative, you're an ion. If you have fewer electrons, well, then you're positive as an atom. So, generally speaking, we represent the atoms as having the same number of electrons as protons. And just keep that in mind because it'll come up here later. Now, as I said, the nuclear model that I just showed you, this is an outdated form of what an an atom looks like. The actual truth of what atoms look like is something more to the quantum model here. And you notice the old model that I just showed you, it has those electrons like spinning around like planets around the sun. And again, like I said, that's not necessarily accurate. These little electrons are actually blipping here and out here and then over here and then over here and then over here. They're all over the place. And what they do is they kind of create a cloudy-like layer around the nucleus of the atom. So the quantum model is our most current model for atoms. And the cool thing is that we actually have photographic proof of this now. Because when you look at atoms under an electron scanning microscope, you actually see these fuzzy structures that kind of show you that electron cloud. So what you see here are carbon atoms, and I'll do a different color so it doesn't blend in. So this over here, you can see this little honeycomb structure. These are carbon atoms connected together to create sheets of carbon layers. So what you're actually looking at is pencil lead, graphite. And what you have are layers of carbon that arrange themselves in sheets like this. They stack on top of each other in little layers like that. And as you draw with your pencil, you leave behind those layers. You're just kind of like spreading out each layer of the graphite matrix here, the honeycomb matrix that you see. So this is actually, I mean, you can see there's an atom, 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 and they're all connected in that little honeycomb structure. So this is how things bond together. And if you look at any substance, any your desk, metal, whatever, if you get close enough down in on it, you will see these little fuzzy things all stuck together in different repeating patterns. So those are atoms. Now, there are different types of atoms, as I said before, and those are called the elements. And a lot of you guys have seen this stuff back when you were in middle school and maybe even when you were in elementary school to some extent. So you can see here the periodic table of elements. We have something like 118 elements today. Most of the ones down here, actually all of the ones down here, are radioactive. These are the lanthanides and the actinide series. So things like uranium and plutonium, things that we can create nuclear bombs with. They have really, really, really big atoms. Those are down there. The ones that we mainly come in contact with on a day-to-day basis are up here. So, and then, you know, sometimes gold and mercury, but for the most part, most of the matter you come in contact with is on that upper part of the chart, and really all the way up to iron, but I'm not going to get into that. So each one of these things, we're going to get into the periodic table, but each one of these groups, you notice they're all colored the same. These all have properties that are similar. So oxygen, sulfur, selenium, tellurium, polonium, livermorium, these all have similar properties. And same thing with nitrogen, phosphorus, arsenic, antimony, bismuth, moscovium. They all have similar properties. So this thing is arranged based on shared groups, and it actually has to do with something, or has to do with how many protons and neutrons are in there and how many electrons are floating around on the outside, and we'll get into all of that when we go into the periodic table. But I just wanted to point out, periodic table, all the different types of atoms. You cannot split a helium atom without destroying the atom itself. So once you get down to a single helium atom, that's as far as you can go. Okay? All right. So there's that. Fun stuff. Now, when you look at the periodic table, you'll notice that all of these things have what is called an atomic symbol. And the atomic symbol is the little square thing with the Zn for zinc. So you'll notice Zn, the first letter is always capital. The second letter, if there is a second letter, is always lowercase. Okay? So that's how you can put these things together and know if you've got an individual atom and it doesn't run in together as words, right? Okay. So the second letter is always lowercase. Now, you have two numbers that are generally represented on your atomic symbol. You have a whole number, which is always the atomic number. Now, sometimes this will be down here at the bottom, sometimes it'll be at the top. It moves over, it moves all around. The thing you need to remember is the whole number, the one that doesn't have a decimal point, is the atomic number. And it tells you how many protons are in the nucleus. So aluminum has 13 protons in the nucleus. Now remember, you also have the same number of electrons. So aluminum also has 13 electrons. It can get a little confusing, so that's why we're going to practice this week. Now, the atomic mass, which is the one with decimal points, I'll use yellow so it draws your attention a little bit more. The one that uses the decimal points, that is protons plus neutrons. That's the weight of the atom itself. And we can do some mathematical wizardry to figure out how many atoms are in, say, a MacBook Air's worth of aluminum, right? We can actually figure that out. But, and that's based on the atomic mass. Now, you'll notice it's 26.98. You can't have 0.98 neutrons or protons. What this is an average. So no matter what, if I'm aluminum, I have to have 13 protons. But I don't always have to have 13 neutrons. Remember, I told you you can have more neutrons than you do protons. So what you see down here on the atomic mass, this is an average. So on average, aluminum has 13 protons, but 14 neutrons, because it's closer to 27 than it is 26. If it was 26, it'd be 13 protons, 13 neutrons. But because it's almost 27, that lets you know that most of the time in nature, aluminum has 13 protons, 14 neutrons. Okay, it's an average. So that's how we get that decimal place. Sometimes aluminum will have 13 and 13, right? But most of the time it has 13 protons, 14 neutrons. So, and how much more often is indicated in that average there. So that's what you're looking at. Now, as I said before, this number corresponds to the number of protons, okay? And since you always have the same number of protons as you do electrons, it also lets you know the number of electrons. Okay, to find out how many neutrons you have, you simply take the atomic mass and you subtract the atomic number. And then whatever your answer is at the end, that's how many neutrons you have. And again, like I said, you can't have 13.98 neutrons, so you round up, and that tells you that most of the time you have 14. Now, if this came out to be, say, 13.4, well, then that would mean that most of the time, or a little less than half, or a little more than half the time, it's 13 and 13, right? So that average can let you know what the predilection is for the element itself, how often it shows up. And again, electrons, just to show you, also that number there. All right, so aluminum, 13 protons, most of the time 14 neutrons, and 13 electrons. And we got all of that from these two numbers right here. All right, fun stuff. Now, one final thing, and we'll get into this in more detail when we get to actual covalent bonding and stuff, but the first layer of electrons can only hold 2. After that, you can hold 8 in each shell. So you'll notice the next layer has 8, and then the next layer only has 3 because it's missing 5. So if you count all these up, it adds up to 13, right? Here's 2, there's 8, and then there's 3 floating around. That comes out to be 13 electrons. So inner shell can only hold 2. After that, it's 8. All right, last thing I'll mention about that. So periodic table, fun stuff, lots of different elements. Now we can mix these elements together, have them bond together to create molecules. So we'll go from atoms, which are just single little tiny things with a nucleus and an electron floating around, to taking 2 of them and sticking them together. And when you do that, you create a molecule. So a molecule is just a group of 2 or more atoms that have been bonded together. So you have some examples over here. Oxygen is a molecule. Hydrogen is a molecule, because these things don't occur by themselves. Like hydrogen wants to bond with another hydrogen. Oxygen pretty much always is stuck together with another oxygen. So you always have O2 floating around. So these are molecules. Now, a compound is a molecule of 2 or more elements in a fixed ratio. So the difference is, with a molecule, you only have to have 2 atoms stuck together, now you're a molecule. With a compound, you have to have 2 different elements. So a molecule is anything where you have more than 1 atom stuck together, but a compound is more specific. You have to have 2 different types, at least, of different elements. So then you have things like water, or you have hydrochloric acid, HCl. Okay, so those would be considered compounds. Now, a compound is a molecule. And you're like, wait, hold on. You're talking in circles, Mr. Clemens. Here's how you think about it. All compounds are molecules, but not all molecules are compounds. The same way that all sharks are fish, but not all fish are sharks. Or all humans are mammals, but not all mammals are human. Okay, so all a compound is more specific. When I say molecule, I'm just talking about 2 atoms stuck together. It could be water. Water is a molecule, but water more specifically is a compound because there's 2 different types of elements in it. That's the minutia. That's the difference there. So there you go. Give you some examples. Hopefully that's clear in your head. Caffeine, for example, everyone's favorite molecule, especially if you're a teacher. Well, it's made up of several different elements. Hydrogen, carbon, oxygen, nitrogen, all of those are inside and in a particular fixed proportion. So anyways, moving on. Now, once you get into molecules, there are different molecular groups. And in chemistry, especially when you get into chemistry in college, you start learning about the different molecular groups. And for example, things like alcohol. All alcohols have an OH at the end of it, and generally it's a chain of carbons and hydrogens. So I'll have a chain of carbon, 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 and here's hydrogens connected. Just like this. And so long as I have an O and an H at the end, well, now I have an alcohol. So there are different types of alcohols. If I just have one CH, so I get rid of these CHs and I just have one CH, well, now I have methanol. So all of the alcohols, they not only share this little factoid here that there's an OH at the end, but they also have very similar characteristics. And in chemistry, you would get to kind of know all of these different groups, how they interact with each other, what makes them that, all of that stuff. Don't worry, we're not going to get into that. This is just an introductory course. So, molecules, there's different groups of them. Now, the cool thing is that if you do a minor tweak to a molecule family, you can potentially change its properties. Or you can just change the look of the molecule and still get the same thing at the end. Maybe one tweak makes it more toxic, but one tweak to the molecule makes it less toxic, but you get the same beneficial effect. I'll get a bit into that in a second. I'll give you some examples. So like I was talking about before with alcohol. So alcohol is represented by ROH. And this R here, that just means a carbon group. Anytime you see R like this, it just means carbon group. So like C's and H's connected to each other. You can have 2, you can have 4, you can have 100, okay? Regardless, if you have 100 C's stuck together and then there's an OH at the end, it's still an alcohol, okay? Now, if you look, all of the examples right here, all of these on this part right here are ethanol. Sorry, they're all 3 carbon molecules. For instance, this one right here, the propyl alcohol, well, that one is arranged in a chain. To whereas the OH is at the very end. Well, on the very next one, the isopropyl alcohol, the OH is up here. So you can move different parts of that around and you will create a different substance. Now, isopropyl alcohol, if you drink it, it will destroy your stomach. Like it's really tough on your gut. It can kill your brain. Your body rapidly absorbs it much, much faster than regular ethanol, the alcohol you would drink. And because of that, you can get alcohol poisoning very quickly by drinking a much smaller amount than you would regular alcohol. And all we did was move the OH over. So we went from having a normal alcohol that you can drink in a moderate amount without causing a lot of damage to suddenly having a much more toxic thing, and all we did was move an OH over to one other carbon instead of having it at the end. So tweaking these molecules can change their effects on your body quite drastically. Another group that I'll talk about very briefly are the esters, and this is what you see up here. So an ester is a carbon group attached to a double bonded oxygen and a carbon with an O and then another carbon group at the end. So what you see, to give you some examples, here's what I'm talking about right there. You see that? That right there is what makes this an ester, okay? Again, down here, there's that structure that makes it an ester. Now you see all of these different examples here, they have different things that are connected to that. And because of that, you might get different chemical properties. So on the examples down here, a lot of your esters are what flavor your food. Well, you can see that peach has an ester that gives it its peach flavor. And oranges have a ester group that give it its orange flavor. And same thing with pineapple and apple and raspberries. So little tiny tweaks to the same base molecule can give you totally different flavors, give you different effects, so on and so forth. And the same thing is true for, say, medicines or drugs. Your cocaine. Believe it or not, lidocaine, the stuff that they inject into your gums when you're getting tooth surgery and stuff, is related. It's in the same family as cocaine. It's just the molecule's been tweaked slightly differently. Amphetamine. So amphetamines are a group of drugs that are generally considered stimulants. Well, if you actually look at the chemistry of amphetamines, well, methamphetamine is exactly like amphetamine. The difference is that the methamphetamine has a methane group at the very end of it, and regular amphetamine doesn't. It has an NH2 at the end of it. So very, very similar drugs, but different effects on the body, different chemical structures just slightly. Amphetamine is also known as Adderall, so it's the drug for attention deficit disorder. So Adderall and methamphetamine, the only difference is instead of having an extra H at the end, well, instead you have one H, but then replacing the other H is a methane at the very end. That's the only difference. Now, pseudoephedrine. So if you take allergy medicine for like a decongestant, you get something that has the D in it, like Claritin D, Allegra D, whatever. That is pseudoephedrine that they have added into that. Well, pseudoephedrine, if you look, has the exact same chemical structure as methamphetamine, but the difference is there's an OH on this second carbon coming off of this ring right here. That's the only difference between Sudafed and meth. So moving a little part of the molecule, tweaking it a little bit, can give you a completely different effect or a different impact on the body, right? And the same thing is true even for the drugs that we use to cure infections like penicillin. Here's a personal example. When I was a kid, I was given penicillin to fight off an infection. That caused hives, rashes, difficulty breathing, and basically I had to go to the hospital because I was having an allergic reaction to it. So here's the penicillin base molecule. Now, what I'm able to take is something in the exact same drug family, which is amoxicillin. It has the same effect on the bacterial infections, but it doesn't give me hives, it doesn't give me respiratory issues, and I don't have an allergic reaction to it. And what's the main difference between them? Well, and amoxicillin has the NH2 attached down here, and on the end of its carbon ring here, it has an OH. Those two tweaks right there to that molecule make it so I don't have an allergic reaction. So anyways, molecules. That's what you're made of. You're a bag of chemistry. Fun stuff. Okay, that brings us into our last subject. So don't worry, I'm almost done. Mixtures and solutions. So this is where we're going to basically leave it off. Mixtures and solutions are not necessarily molecules. There's not necessarily things connected together. So a mixture is a combination of two or more substances where all of the substances keep their original properties. They're not sticking together and bonding together. An example would be like, say, fruit salad or snack mix. If you've ever had Chex Mix or Gardetto's Mix, that would be a mixture. That's why we call it a mix, right? Notice that the little rye crackers and little pretzels and all of those, you can take them out, separate them out again. They're not stuck together. They've maintained their original properties, right? Okay. With a solution, it's a homogeneous mixture. So it's a mixture, but it's homogeneously mixed together and it's not easily separated out. So a solution is when you dissolve something into another thing. So if I take sugar and add it to water and mix it up until you can't see this sugar anymore, basically what's going to happen is all the sugar molecules get dissolved in the water and they mix perfectly evenly throughout the entire liquid. So my sugar water, my Kool-Aid, if you've ever made Kool-Aid, you know that the first glass of Kool-Aid and the last glass of Kool-Aid taste the same. The same thing is true for tea. The same thing is true for coffee or Coca-Cola or whatever it is that you're drinking. It tastes the same from beginning to end. The reason is it's been evenly mixed together. And that's one of the things that makes it a homogeneous mixture. It's evenly mixed throughout. And because one thing dissolved into another, you can't easily separate it out again, it's a solution. Okay? So, some examples. I'm going to move my camera box here so we can see this stuff. Up here at the top, you'll notice every green it comes a red, and they're nicely evenly mixed together. That is what homogeneous looks like if I'm a mixture at the atomic level. Okay? Same thing with your air that you're breathing right now, so on and so forth. A heterogeneous mixture, which is just a normal mixture, that has areas of concentration that might be higher here, might be higher here, not as high over here, so it's unevenly mixed. And heterogeneous mixtures, they tend to be things like oil and water, things that are easily separated again. Cereal and milk. Your cereal sits at the top of your cereal bowl, on top of your milk. When it gets soggy, sometimes it sinks to the bottom, right? So that would be a heterogeneous mixture. Ice would be the same thing. All the ice tends to stick together at the top, and there's water beneath. So that would be considered heterogeneous mixture. You see the examples on your screen. Things like chocolate chip cookies, pizza, tossed salad. All of those things are heterogeneous. They're not evenly mixed together. Okay. And then your homogeneous mixtures are the things like air and vinegar and blood and wine and coffee and Coca-Cola and all those things. Okay? All right. So, with solutions are those homogeneous mixtures. So you notice my examples didn't change here. These are all solutions. So homogeneous mixtures are solutions. And when you look at the parts of a solution, you have two parts of a solution. You have what is called the solute and the solvent. Now, generally the solvent is something like an alcohol or water, things like that. The solute typically is the thing that's being dissolved. So salt would be the solute in salt water, and water would be the solvent. And water is known as the universal solvent because it dissolves most things. So really this is just terminology, but solute, the thing that's being dissolved, solvent, the thing that does the dissolving. Okay? This will become important later on when we're going over mixing things together and creating solutions and all that. If I tell you that you need X amount of solute, that lets you know the solid thing that you're going to be dissolving into the solution, or the solvent. Anyways, minutiae aside, that is a quick intro to some of the things that we'll be talking about in chemistry, give you some things to kind of think about, give you a different way to kind of start looking at the things in your room, the things you interact with on a day-to-day basis. As you start looking around the room, you can start thinking about all the different molecules and mixtures of molecules that create all of the wonderful things in your home. It gives you a different lens to start viewing materials, or your foods, or your drinks, or your medicines, right? So that's that, guys. I don't have a big, wonderful, explosive way to close this out. That's just kind of the material we're going over this week. Going to give you guys some practice on some of the atomic numbers and things like that coming up this week. And I've got a quick little research assignment for you to kind of take a look at one element and kind of get an idea of some of its properties and some of the important things about it, just to kind of get you thinking about elements and atomic properties. So that's it for the week. I hope this was not too confusing. Hopefully I didn't talk myself in circles, or I didn't talk you in circles. And yeah, with that, I will see you guys later. Go Chiefs!